Okay, so welcome to the next lecture of module number 9, that is on D algorithm. So, over the last few lectures what we have seen is that for testing generally the two types of automatic test pattern generation algorithm, if you look at it basically. So, that is random test pattern generation algorithm and another is by path sensitization, that is by actually false, sensitize, propagate and justify. So, by path sensitization method in the last lecture we have discussed that there can be two types of them. So, one is by Boolean difference and one is by the D algorithm, that is by path sensitization, propagation and justification. Also then we have discussed that this Boolean difference, I am sorry, that is Boolean differentiation and all this was a very difficult problem in terms of complexity, because if you go for Boolean difference then there is a you have to go for derivatives and all this. So, it may lead to and the number of test patterns that may result can be exponential in nature. So, due to this exponential large complexity for this Boolean difference based scheme or based algorithms, we have generally shifted to sensitize, propagate and justify approach. Also over the few lectures, I mean over the last few weeks, we have mainly discussed that we have given several examples of sensitize, propagate and justify, in which case also in the last lecture we have seen one example, in which case what we do, we actually if they are stuck at 0 fault, we apply a 1 and vice versa for stuck at the other way, and then we propagate the value to some output and then we try to justify that propagation and sensitizations are justified by some input value. So, this was actually basically the D algorithm. D algorithm is nothing but sensitize, propagate and justify. But in this series 2 lectures we will actually have a very detailed look at them, that is we will go for a very formal way of defining the algorithm, because D algorithm as we will see is one of the most prominent or the background or the backbone of digital testing, because I mean next we will see sequential circuits and several other BIST architectures and all, but for all of them D algorithm is the backbone. From D algorithm there were different other advanced versions of the algorithm like PODEM and FAN, but the basic bottom line or basic backbone which we should learn in detail is the D algorithm, because it was the starting point for all sensitize, propagate and justify based ATPG algorithm, which still occupies the prominent role in digital testing. So, in these 2 lectures what we will do is that we will try to look at this algorithm in a more formal way. So, in the last lecture as we give an example that for a given circuit, say gate, like say if they are stuck at 0 fault, then we apply a 1, then we say that in normal case the answer is 1 and the fault case the answer is 0. So, we could have written this as it could easily solve our automatic test pattern generation problem, but we said that to represent it formally we have to say that we represent it by some kind of a symbol like D. So, that because in Boolean algebra we cannot have A oblique B or 0 oblique 1 or something like that. So, we have gone for a 5 value Roth algebra where we have symbol like D, D prime, X and all. So, that is what is representing the circuit algebra or that fault or the circuit having faults in a more formal way. Similarly, for the D algorithm or sensitize, propagate and justify based approach, till now whatever examples we have studied and all were in a somewhat informal way. In today's lecture and in the next lecture, is lecture 2 and 3 of this module, we will see this in a more formal way, that is our basic approach. Okay. So, first we have already seen about these Roth algebra. Okay. So, I mean that Roth algebra will be used for this what you call this D algorithm. Then before we start discussion on the D algorithm, we will see some basic definitions and procedures, that is very important. Then we can go for the formal algorithm, and finally we will see that some advanced algorithm like PODEM and FAN. So, just we will see the basics of them. They were all advanced versions of D algorithm, but as I already told you that D algorithm was the basic backbone. From there we have developed so many advanced algorithms, but the starting point was D algorithm for all these sensitize, propagate and justify based approach. So, it forms the background. So, this is what is the basic plan of the next 2 lectures. So, first before starting the algorithm, as we told that we will go for some of the definitions and procedures. So, first definition is the singular cover. Okay, so, what is the idea? So, let us first read the definition and then I will try to explain you. Singular cover of a logic gate is the minimal set of input signal assignments needed to represent the essential prime implicants in the Karnaugh map of the logic gate, both for case 0 and 1. Okay, so, now let us see what does that mean. So, let us take the case 0. So, let us say that what do you mean by prime implicants? Already we have seen in our discussion during the design part of the course, because we know that this course is on design, verification and test. So, in the design module of this course we have discussed in details what is a prime implicant. So, we say that whenever we have a Boolean function, we represent it as equal to say A B plus C D prime plus F, something like this. So, if you say that is a prime implicant, then this one should not be contained in any of them, as well as it should contain an implicant which is neither in this nor in this, that is it contains some mean term which is in neither of the other implicants of the function. So, this is a very informal kind of way of stating, but already we have discussed this in detail in the design module. So, in other way speaking, that this implicant is mandatory to be present in this function representation, because it has a prime mean term which is neither in this neither in this, something like this. So, it has to be present, though it is actually sometimes called the essential prime implicant, then it is mandatory to be present. But in case of prime implicant, what is the idea that say it is like a b plus c d or something like this plus f, some function, then it should not be contained directly in any one of them. Like if we can say that we have a function like a b plus b, sorry, a b plus b, then what does it mean that a b plus b? Then what does it mean that this a b is actually contained in b, because a b is actually a b plus a prime b. So, this a b is contained in b. So, then we can say that a b is not required, because b actually represents the case of a b. So, this is some of the definitions of prime implicant and essential prime implicants which we already discussed. So, basic idea is that we have to first select the prime implicants, and then say for the case 0, then we have to find out that is the minimal set of input assignments needed to represent the essential and prime implicants in case of 0 and 1. So, let us take the case of 0, say. So, and in the case of an AND gate. Okay, so, AND gate 0. Now, you say how we can get 0 in case of an AND gate? We can get the 0 if the answer is 0 0, 0 1 and 1 0. So, these are the 3 cases in which case we can say that the answer is 0 for an AND gate. So, now we can represent this by 0x or x 0, and because this 1 0 and say sorry, I mean let us represent, these are the 3 cases which represent that the output of the AND gate is 0. So, now if you want to represent this as a prime implicant case, okay, so we can write it as x 0 and 0x, because this 0 0 is included here, is also here. In this case it is 1 0 is included over here. So, this comprises 0 1 and sorry, this 0x incorporates 0 0 and 1 0, correct. And if you take the other case, that is if you take the case of 0 x, then it comprises 0 0 and 0 1. So, basically this 0 0 0 and 1 0, 3 you do not require to represent because of the case, then it will no longer be that prime implicant case. So, we can represent it as x 0 and 0 x. So, it x 0 and 0 x. So, if that is actually you can say if it is in terms of a and b, then you can say that it is b prime plus a prime kind of a thing you can write, okay, because this is 0 and the other part is do not care, that is x a b prime plus a prime b. This other part is not is hyphen or it is do not care kind of a thing. Okay, so, that is why we represent x 0 and this one. So, because if you take these 2 combinations, then automatically in these 2 cases we have 0 0 0 1 and 1 0. These 3 bits, these 3 are actually included in these 2 cover. So, now we can say that these 2 are actually form a singular cover for the case 0, because you do not require to represent this one and this one, because this 2 is comprised over here, that is 0 x, and this one actually 0 0 and 1 0 are actually comprised in this one. So, this 2 actually 0 x and x 0 becomes the singular cover for 0 of an AND gate. For the OR gate, we know that it is always the dual. So, OR gate output is 1 when OR gate output is 1 when we have 0 1 or 1 0 or 1 1. So, it is better to represent it as 1 x and x 1, because these 2 will actually form the essential cover, because these 2 are prime implicants, because this is neither contained in this and this is neither contained in this. This one have one element at least which is not contained in the other. So, that is 1 x plus x 1. Actually, if you write a function like this, that is say for the OR gate you write it as a plus b, that is actually b, that is a hash dash b, that is actually you can better write in this way, that the function is something like f equal to a, then we do not write anything, then plus we do not write anything, then b, that is actually 1, this in this 1 you do not care and this do not care and x. So, these are 2 if you take, then it comprises all the 3 cases 0 1, 1 0 and 1 1, which is representing 1 in case of a OR gate. So, I mean these 2 actually forms the singular cover for 1 in case of an OR gate. Okay. So, now if you look at it for the 1, if you look at it for the AND gate, when you can get the cases of 1. So, there is only one combination, that is 1 1 when you get the 1 in the AND gate and 0 0 in the case of an OR gate. So, this will actually form the singular cover for the OR gate, and this will for the this will form the singular cover for 1 in case of AND gate, and this is for the 0 in case of an OR gate, they are both dual of each other. So, basically what actually the singular cover says that, so if you want to get the output 0 in case of an AND gate, so you can either use this or you can either use this. Similarly, this is for 1, and for 1 in case of a AND gate, this is the combination required, and for OR gate 0, this is the combination required. That is actually singular cover means a minimal set of inputs, that is this is actually in other words we say that what is the minimal set of inputs to represent a output 0 at AND gate. You can say that only one input is 0, that is the minimal set, and you can also say that this input is 0, other is do not care. So, these are the two minimal sets which represents the output to be 0 in case of an OR gate, and this can be extrapolated for an OR gate. So, this is the basic definition of a singular cover. Now, we go for the second definition, that is called the D frontier. So, all these definitions we are looking at will be required in the formal representation of a D algorithm. So, now what is a D frontier? So, we know that D basically the term was introduced because D represents 1 0, that is normal case, fault case, 0 1, that is actually you can also say D prime, normal case and a fault case. So, this was actually Roth's 5 valued algebra we have already seen. So, this is the represent that was actually used for representing the fault in a circuit. Now, let us see what is a D frontier. So, let us read the definition. The definition says that the D frontier comprise gates whose output value is x, we do not know the value yet, and at least one of its input is D or D prime. That is, we have a gate something like this. So, this is either D or maybe D prime whatever, and the output is x, maybe one other input. I mean, we are not talking about the other input. This implies that any gate in D frontier can be used for fault propagation. Let us now look at what is this meaning, what does this definition mean, because this is one of the most important definition, or you can say notion to be used in the D algorithm. It says that, say for example, we have a gate like this, when OR gate AND gate like this. So, and this is say initially all the nodes are say x, okay, we do not know, say for the time being. Okay, now we say that this is D, that means what, normal case 1 and fault case 0, that means this line is capable of propagating the fault output. Now, if I know that this output is x, that means as of now I do not know the value, that means still you have a scope that this value can be D can be propagated over here if you apply a 1 over here. That means this AND gate is capable of for fault propagation. But on the other hand, if you see there is a gate something like this, say for example, we have the same AND gate, we have a D over here and the output here is 1 and the output here is 1. So, this is not x, it is not the x, that means what? Now, this is 1, so this has become, sorry, this is 0, I am sorry, this is 0 and this is not x, this is not x, because if it is 0, then this will be 0 and not x, this is not it will not be x, then what is the case? Then D cannot be propagated over here. So, what does it mean? A gate in the D frontier can only be used for propagating the effect of the fault, that is either D or D prime. Let us see this example of the circuit. So, let us know that there is stuck at 0 fault here. So, obviously, you have to sensitize, so you put a 1 over here. Now, what you do? So, one more thing is that whenever you start a circuit analysis, you make all the input, I mean all the net lengths as x initially. Okay, so, all the lines as x, because we say that we do not know the value. Slowly whenever we will start knowing the value of the nets, we will try to fill that from x to we can say that 1 0 D or D prime as we start computing the values. So, it is a stuck at 0, so your input is 1. So, this is D because normal case 1, fault case 0. So, it is a D over here and a D over here. And we know that this input is x, this input is y, this input is x, because as of now we have not computed the value of x. So, the output of this AND gate is x, because if it is a x, if this is a x, if it is 1, then you get the value of here D, and if this x is 0, then you get the value 0. So, as of now we do not know the value of x. Similarly, this is an AND gate. So, if the C is equal to 1, then we get a D prime here. If Cx is a 0, then we get the 1 here. But as C is yet an x over here, so this value is also x. So, these are the two gates, because the output here is x and x. So, these are the two gates which actually comprise the D frontier, that is this fault effect can be propagated via this one or via this one, because they are the actually this comprises the D frontier, that is these gates will allow you, that is this gate 1 and 2 you can say comprises the D frontier, because they can allow you to propagate the fault effect. But maybe you think because of some reason or the other that C has become a 0. If C has become a 0, then immediately this will not be x, it will be 1, then 2 will not be in the for D frontier, because D cannot be propagated through this gate number 2. So, that is what we actually say that whenever a gate is in the D frontier, then only it can be used for propagating the value of the output of the circuit, fault effect of the circuit. That is, what is the basic idea? The basic idea is that x at the inputs can be appropriately selected, so that d or d prime can be computed at the output of the gates. That is the basic idea. That is, so this x and this x can be controlled in such a way, so that this effect of d and here d prime can be propagated out the output of these gates, which comprises the d frontier. So we can, if there is a gate in the d frontier, then we have a scope that we can set this value appropriately or accordingly, so that the fault effect can be propagated to the gates in the d frontier. So once the is very important. So once the fault effect is propagated, that is, say fault effect is propagated by making this as 1, then this one will no longer be in the d frontier, because already you have used this gate and the fault effect has been propagated. So this cannot be again used for propagating another fault effect. So it is to be deleted from the d frontier. That is the basic notion here, this second definition. Okay. Okay, now there is the next definition number 3, that is called unique D drive. So now what is a unique D drive? Then it is actually called, if there is only one gate in the D frontier, then it is actually a what do you call a unique D drive. This situation, because it can be then propagated to only one input. So let us just see what is a unique D drive. The definition is very straightforward. Say for some example, say for due to some reason or something like this, let us say that these two lines were short, for some reason. Okay, then what? And let us consider that this was a stuck at one fold. Let us just change this one. Then what happens? To sensitize this stuck at one fold, you have to apply a 0 over here. So moment you apply a 0, so C will be 0. So moment you apply a 0, you will get the 1 over here. But in this case, this is D, it will not be D, it will be a D prime, and this will be a D prime, because normal case 0, fault case 1. And then if you want to affect, and this case will be still 0, so this is no 0, this is 1 because this is 0. Now this AND gate output will be still an X, because if you apply X is equal to 1, then you get a D over here. If you get a 0, you will get a 0 over. So there is a scope of propagating the fault this one. But there is only one gate, that is only this gate is in the D frontier, this gate is not in the D frontier. So it has a unique gate from which the fault effect has to be propagated. So this situation is called the unique D drive. That is, there is only one gate in the D frontier which can be used for propagating the value of fault effect. So if for a fault there is a unique D drive, then you do not have to think for what are the choices. Just like we have seen in the last example that always, or we will be also looking in details in this lecture or in the next lecture, that D algorithm like sensitize, propagate and justify is always not a successful case. Sometimes you will, if they like in the last example, we had two D frontiers, like this one. If you have gone for the general case, that is if you have just gone for this non-modified case, then what is the idea? So if you have gone for the non-modified case, then you have these two gates in the D frontier, this gate and this gate in the D frontier. Now it is up to you that whether you select this gate as the D frontier or this gate as the D frontier to propagate the value of the fault. Now once you have selected this gate for fault propagation, then this is deleted. But there is option 1 and option 2. So sometimes one of the option may give you a correct result, and correct result means inconsistency, that is there will be no inconsistency. You can finally propagate the fault effect to the output, as well as you can also justify this. But for some of the selections of the D frontier, if there is a multiple choice available, like in this case there was 2 gates, so you may land into a problem, because by propagation in one of the gates you may land to a inconsistent situation, that is fault can be propagated but it cannot be justified. So if there is a unique D drive, then there is no such option to think about, because there is only one drive. So you have to just drive the value using that gate. So unique means there is no choice at that point. Okay. So now let us look at the next definition, that is definition 4, it is about J frontier. So there are two frontiers that is mainly used in D algorithm. One is called the D frontier and one is the J frontier. So basically you can remember in this way. So D frontier means what? That is you are propagating the value of the effect, that is D effect, from input to output. So that is what is basically you are doing. So if you are using a D frontier algorithm, so D algorithm, D frontier definition if you think, so it is taking the value of some D or D prime, that is fault effect, and you are trying to propagate it to the output by gates having whose output is X. Okay, so that is input to output. Now this is actually called the propagation. So D frontier is basically related to propagation. Now there is something also we know, that is justification. So once you have, say for example, propagated the value up to here. Okay, now also it is our duty to see that this line, this net and this net are properly justified, so that the propagation and sensitization are successful. So J algorithm, as we will, J frontier, as we will see now, is basically related to the justification procedure, and it works backward. It works from primary out to input, so backward direction. Now so let us first read the definition and then we will look at the meaning and implication. So the D frontier, what it is saying, the J frontier, what it is saying, the J frontier comprise gates whose output value is known, either 0 or 1, but the its inputs are not yet computed or not yet implied by its inputs. In other words, the output of a gate in the J frontier is known, but its input is not yet computed. That is, it implies that any gate in J frontier can be used for justification. That means what? Say for some reason you know the value of this one is to be 1 or 0 or 1, whatever, you know that I have to get at this one. Sorry, you should not write 0/1. So, you know that I must get a value of 0 in this, I must get a value of 1 in this, and something like this. But now this is known, but from that this is already known, but these two inputs are, say this is x and this is also x. The inputs are not yet computed, but not yet implied by the input, that is, the inputs are not yet known, or at least one of its input is not yet known. That is, we know that this is, say or 0, so this we know that this is 0 for some but this is x. That means, to justify the value of x here, we know that x has to be computed to 0. That is, in this gate what happens, the output is known, either one or both of its inputs are still x. That means, this gate still has a scope that the 0 can be justified over here. So, let us, we will take this bigger example a bit later. So, let us just take a very simple gate and understand the concept. So, let us take this case. So, we say that the output here is a 1. Okay, and for the time being, let us assume that the inputs are x and x. So, we know that this gate can be in a J frontier because we know that the output is 1. Now, for make this successful, we require this one to be 1 and this one to be a 1. Okay. Because this may be for requirement. Okay, this may be requirement because, say, it may be driving some stuck at 0 fault. So, it is masked that it has to be 1, so that the fault can be sensitized. So, this x and x equal to 1 and this also x equal to 1, you can make that and it can be successful. Okay, now let us see for some reason both these inputs are 0 and 0, for some reason you can think, because of some other implication and some other set is 0. Now, this is 1 and this is not x and this is also, these things are not x, then this cannot be in the J frontier. Why this cannot be in the J frontier? Because this is stuck at 0 and these inputs are not x. So, that means there is no scope that you can control this gate, so to get the value of a 1 over here. So, this for this gate the justification procedure is stopped. Okay, in other words, say for example, there can be also another case like this, this is stuck at 1 and this is 0, you have to apply. Say you know this is x and this is 1. Okay, so this gets still from the J frontier because we know that still this x is with you, you can control this x and you can apply it 0, so that you can successfully control, you get justify this value. Okay, so there is one x, that means sometimes you can be possible to justify it and sometimes it may not be. Like for example, I mean a gate in the J frontier always does not mean that it will be successful in justification. Okay, but it may be, like in the last case it was, but now in this case let us say that it is stuck at 0, so you have to apply a 1. So, this is 0 and say this is x for some reason. This is 0 because of some other reason like fault sensitization or some other case because of some other, these are some other inputs are there, for some reason it is 0. So, this is x. So, this is in the J frontier because this is x. So, you may think that there is a scope that this x can be controlled, so that the output is 1. So, you will try to apply this as 1, but because this net is input is 0, so you can never get a 0 over here. So, this gate is in the J frontier, but it is not successfully allowing you to propagate the justify the value at the output of the AND gate. So, a gate is in the J frontier means at least one input is 0, one input is x of the gate, but it does not just imply that always it will be successful in when you call justifying the output of the gate, but at least whose inputs are not known, the output is known, that is output is known means that is the requirement, and inputs are not known means that you have to compute the inputs from where, from the requirements of the justification algorithm, you have to find out that is one. So, if you have a gate whose output is known, but inputs are not yet known and they have to be computed, so you can think that that gate can be used for justification. So, that gate falls in the J frontier. Like in this case, say what do you say, just take an example. In this case, if you see what do you want over here. So, output of the gates are known. Say for example, in this case let us think that this is 0 D, okay, because this gate D has to be propagated over here, correct. So, also this gate has to be propagated over here. Now, if you look at this gate, so what do you know? We know that in this case, say for example, because of the D frontier, so this initially both of these were in D frontier, so somebody has selected that this should be the D frontier and not this. So, let us keep it as an X. So, we are not yet selecting this one. So, let us think that this we have been selected as the D frontier, this is not been selected. So, once this is selected for the D frontier, so what is going to happen? So, this one will be X will be converted to D, and because it is non-inverting gate, and sorry, this is not D, this is X, because this gate is not selected by the D frontier for the fault propagation, this one. Now what happens? So in this class just look at this gate. So output is known to be D, one of the inputs we know is to be D, other input is X. So this gate will lie in the J frontier, because now this is D, this is D, and we need to find out what is the X. That means this you are going backward, and still this gate has a scope of justifying the output of D over here. So obviously we know that X equal to 1. So you select X equal to 1, then this input actually justifies the propagation of this one. So this gate falls in the J frontier. So what we have done, initially we know that if you just look at this case, so this is also X, let us think, this is wrong, I mean for the typo this is X actually. So initially everything is X, so you apply stuck at 0 1, so D and D over here. So we select this for the D frontier, this one is also D frontier, this one is also D frontier, because in these two gates you can propagate this value of this D through this. So both of them are D frontiers. So let us select this one as the D frontier. So once you do that, the value of D is coming over here. Now this X is gone, but this still remains an X, because this is not selected as the D frontier. Now once it is selected as the D frontier, the output is known. So once the output is known, this input is X. So you can now the basic idea of the J frontier is that you can select this appropriately to be 1 or 0, whatever be the case, so that this output is justified over here. So this actually, this gate as the input is 1, so it is actually, you can be used for justification of your approach. So this actually falls in the J frontier if actually this is actually gate is taken as the D frontier. Okay, so the output is known and input you can compute. For sometimes, I mean always you should not think in that way that this gate is in the J frontier, so it can be used for the propagation, that is fine, but sometimes the gate not also being in the J frontier can do your job, maybe because of some other reasons of some other input, say that it automatically becomes 1. So in this case what happens, this gate may not be in the J frontier, but still it is justifying your output. So this may also be the case. Okay, also for the sometime it may also happen that this X is 0 for some reason, then this case D cannot be propagated over here. In that case this does not remain in a J frontier and it does not serve your purpose. Okay, so a gate being in D frontier, you can say many things. So this gate is in D frontier, that means you can say that I can use, this gate is in D frontier, that means you can use this for justification. But a gate in not D frontier does not imply much. So a gate not in D frontier, say A equal to 1, then it will help you to justify automatically. This is 0, the gate is not in the D frontier, because if X is 0 or 1 already predefined, then both the inputs are known and the output is also known. So you cannot, it is not be in the J frontier. So sometimes it may help you, if it is 0 then it will not help you because D cannot be propagated, and if it is 1 it can help you because D can be propagated. Then it does not remain in a J frontier. So a gate not in a J frontier may or may not help you, that depends on situation to situation. But if a gate, this gate is in a D frontier because this is known and this is X, then if a gate is in J frontier, I was talking about the J frontier. So if a gate is in J frontier, then it can be used to find out that whether it can be used for justification or not. So a gate not in J frontier, it may help or may not help. A gate in J frontier means you can study that it can be used for justifying your approach. So sometimes you may be successful, sometimes it may not be successful. But whatever gates are in J frontier, that can be used for justifying your input. So for what we do, basically we propagate the fault to the D frontiers, and then we reach the primary output, and then once we have reached the primary output, the fault effect, then we find out which are the gates which are in J frontier. Okay, and then we try to justify using the J frontier. So we will take some complete examples in the next lecture, so which will allow you to understand the concept better. So I mean whatever we were saying is that this last example which we said that assume that it was decided that the fault effect will be propagated via J. So that is we are actually affecting the the same example actually, may not, the same idea is there. We may not go for this one, the same thing we have discussed about the J frontier and the D frontier. So this thing is elaborated in a detailed manner over here. Okay, so this example is detailed over in this slide, so you can see. Okay, so now we will go to the D algorithm, that is another, we were looking at some definitions. Now we will see some procedure, that is some sub algorithm or sub steps of this one. So first sub step is called the implication. So implication actually procedure is a procedure or a sub-module of the D algorithm. It comprises 3 steps. Compute all the values of the signals that can be derived uniquely from the given signal below some net. If many choices are available, for example a singular cover, any one of them is be considered. So what we do, okay, then let us see the next step and then we will come back. Maintain J and D frontiers and then check for inconsistencies, stop in case of inconsistency, that is contradiction. Basically the implication procedure is similar to simulation procedure, where all the nets are determined starting from the primary input to the output. So what basically implication does? So we try to find out compute the all values of the signals that can be determined uniquely from the given signal value of some nets. That is, say for example, we will take this one. Okay, so that means what? So initially everything is x. Initially when you start your design or start your implication procedure, everything is x over there. Then what we do? Say for example, we apply a b over here. Okay, so this stuck at 0, so we know that b has to be 1 has to be applied. Now once b is 1 is applied, then what we know that immediately these two are d and d. Okay, but we do not know the value of C, D and A because they have to be determined by using D frontiers and J frontier. Okay, but immediately we know that these are D and D. So for example, also if you think that that there was another, say also let us take the other way. So let us not take the fault over here. So let us take the fault, say here, stuck at 0 in this net. So what happens? We know that B has to be 1 has to be applied. So immediately B has applied, we know that this is D. So this is the implication procedure. And also if to sensitize this we apply a 1, so immediately we know that this value will be a 1. So that is, but others we cannot compute because for others we have to know the D frontier and the J frontier. So, for some of the values by the sensitization process or some other mechanism, what happens that once you set the value for some reason, like in this case you have set the value of 1, then automatically this is stuck at 0, so it will be 0, and this net does not have any fault, I mean because we know that in case of fan out circuit, so this net and these nets are actually independent of each other. So if the net number I is independent of net number E, then actually this value can be directly incorporated from here. Now why it can be incorporated? Because we know that if B equal to 1, then immediately this I will be equal to 1 because the fault is in the other branch of the fan out. So this actually comprises your what do you call this this is implication procedure. That is, circuit initially will have some, all the nets will be set as x. Now next what you have to do, you have to just find out that what you have to find out that some of the net values if you can directly compute, like in this case 1 can be directly computed over here. So this is called the implication. But the value of f, the value at j, or the value of g, the value of h, this cannot be computed directly, because for that what you have to do, you have to first find out whether you will use because if you are having a stuck at 0 fault at E, then what happens? Then your F, this gate actually, this is the only gate, this will only become your D frontier. Then you actually have to propagate the value of D through F. So once you have propagated the value of D through F, then you know that this gate will become your J frontier, and then you have to find out that whether what is the value of X. So X you cannot, it is difficult to directly get it by implication, because if by implication what we do is that what we do is that by implication we just find out the values which can be known directly. Okay, so that was the first step we discussed, that compute the values of all the signals and can be determined uniquely from the given signal values of some nets. If many choices are available, for example in case of singular cover, if many choices are like for example you have a AND gate whose output is actually 0 for some reason. So we know that the inputs can be, or the implication can be x0 or 0x, so you can take any one of them, that is what is being said. So if the multiple choices available, you can take any one of them and they get very considered. So then from once you have done this implication, then you can also find out that what are the J frontiers and what are the D frontiers. Basically we first find out what are the D frontiers, that is how you propagate the value, then you can get the J frontiers out of it. So if there is some inconsistency means that you want the value to be 1 for some net, and because of this what is the implication and all, you get the value to be 0, then actually it is an inconsistent, you have to stop. So basically implication procedure to simulation procedure where the values of nets are determined starting from the primary input. So it is just like a simulation. In simulation what we do, we know the inputs and we try to compute the output. So we have seen in the last 2 to 3 lectures back that event driven simulation we have seen, compiled code simulation we have seen. So in that case what we do, we give some input to the circuit and we try to find out what is the output of the circuit. That is basically the idea. So in this case also what happens, we try to, because there is fault in the circuit, so what we do is that we first find out, we sensitize, maybe we first sensitize the fault, then for initially all the nets of the circuit are having X, then we sensitize the fault, then we try to find out which nets of the circuit can be determined 0 or 1 or D prime by this value. So once some of the nets have been determined, step 1, then if there is multiple choice, you can take any choice of them like X0, 1X, 0, 1, 0, 0, whatever. If some multiple choices are there like 0X, X0, 1X, X1, something like this. So for the AND gate and OR gate kind of thing, that is by the primary input cover we have seen. So, any one of the choices you can take, and then we try to get the D frontier and the J frontier, all these things you can find out, then you can go for justification and all. So, we try to find out as many values of the nets uniquely as possible, but at every step we maintain the J frontier and the D frontier, that is very important. And also if there is some inconsistency, like same net you have to apply 2 values, then I mean once we say that it is to be 0, and by what they call implication it gets the value 1 and vice versa. So, you have to stop at this time and say that it is an inconsistency. So, this implication actually is you can call a very important module of the D algorithm. So, when we will be looking at the D algorithm in detail, so we will in a more formal way we will see how it fits to, but basically this is the heart of the D algorithm, that is you first uniquely determine what the value of the signals, maintain J frontier and D frontier, and then in case of D algorithm you have to add 2 more points, that is if there are n number of D frontiers, so you have to take, if there are n gates in a D frontier, then you have to take any one of them, and then you have to go for the J frontier justification, and if you keep on doing it till your D frontier reach the primary output. So, basically we will see that this implication is basically the heart of D algorithm. So, but there is slight difference between simulation and implication, let us see. So, in each case, all this, in case of simulation all the values are determined uniquely, because there is some primary input, obviously your circuit will have some primary output, because there is no choice. You have for an AND gate, if your input is 0 0 you get the answer 0, if your input is 1 1 you get the answer 1. So, there is nothing called x 0 x 1, all these things are not in simulation. Simulation you have simple inputs, so you get the simple output. But in case of implication, some signal values may not be determined uniquely. Why? Because already we have seen that for a AND gate if the output is 0, so you take x 0 or 0 x. So, we can also take 0 0, but we generally do not take 0 0, because there is a problem which we will see later. Okay, that we will see later why you not take it. So, that is one thing. So, in case of implication, some of the values may be x, we are not determined uniquely. So, the value of assignment moves from input to output in simulation. So, in simulation primary inputs you give 1 0 1 1, then there is the circuit, and then you compute the output. So, that is a very simple. So, in case of implication, what we do, it is not a unidirectional flow, that is we do not flow from straight this one to input to output, but rather what we do, we first find out that some point we find out some fault is there, then we sensitize it, then we find out the D frontier. So, D frontier will propagate the value, then once the D frontier propagates the value, some J frontiers may be created. For in the J frontiers you have to justify the justify the inputs, and then again a new D frontier is created, and similarly we take the D value to the output, and at every step one step when you are propagating the D value, at the same time you are trying to justify the the value of D is being propagated. So, also we try to justify the values using the inputs of the gate in the J frontier. So, it is actually it propagates both ways, primary inputs and outputs. For example, to take a stack at 1 at net A, we have 2 implications: backward to make the primary input to D0 and forward to the primary output to D. That is what it is actually saying, that if you have an AND gate, so this one, so this is actually stuck at 1, so you apply a 0 over here. So, this is a forward direction you can say, that because we can consider this to be the D frontier, so it will be actually D prime in this case, because normal case 0, fault case 1, stuck at 1. Now, we have to again, so once this is 0, this is D, or do we know the output to be D, that is normal case 0, fault case 1, sorry D prime, normal case 0 and fault case. So, I am just sorry. So, this was talking about the AND gate. So, in the AND gate this is stuck at 1. So, you apply a 0 over, you need a 0 over here. So, it is normal case it is 0, fault case it is 1. So, this is D prime. So, we know the value of the output to be D prime, and both the inputs are x. So, it has to be output should be 0. So, you can have x 0 or 0 x, any one of them is fine. Okay. So, that is what he is saying, that in case of simulation we if we have 0 0 at the input of the AND gate, we get the output as 0. So, it is a unidirectional flow, but in case of the implication it is a both way. First we have to sensitize this fault, then it actually become the D frontier kind of a thing. So, you get the value of D. Now, again we justify this one. So, this because it becomes the J frontier. So, it is actually moving backward and forward. So, backwards to make the primary input 0, forward to propagate the primary output, this D prime has to be propagated to some primary output. Okay. So, in case of implication, sometimes we have to sensitize the fault and then move the fault value to the output, that is forward direction, and backward direction, because once the D frontiers are done you get some J frontiers. So, you have to take the value backward, and this is, and that is for justification. So, this is why there is a difference between simulation and implication. Another difference is, in case of simulation there is no inconsistency, because you give an input and the output you can determine uniquely. correct, and there is no concept of any inconsistency. But in case of a implication, then there is lot of inconsistencies can be there, because if the same net you have to assign a 0 and then you have to assign a 1. So, same net, I mean, while you are propagating the fault value, then you say that you have to assign a 1, and but for justification case it says that you have to apply a 0. Such cases we have already seen in the last lecture, and also we will be seeing in details in the next lecture. So, then it will say that it is inconsistency. But in case of simulation, there is no questions of any kind of inconsistency, because some inputs are there, you get the output, a unique output. Okay. So, now let us see some examples of the definitions and the procedures we have seen, because they are somewhat bit complex. Okay. So, we will just try to illustrate that with some examples. Okay. So, in this case, say this is a AND gate. So, the output is 1. So, when the output is known, say the inputs are x and x. So, if the output is known, then we say that this is actually a J frontier. J frontiers means, I already told you that output is known, but in both the inputs or single input may be x. So, we know that if the output has to be 1, both of them has to be 1 1, because that can be covered from the first, I mean what you call this first, I mean the slide we have shown, first or the second slide, that is on singular cover, that is for 1 1 in case of an AND gate, this is the singular cover. So, that is actually you have to know this table when you are doing this J frontier and D frontier business. So, this is a 1 1 for this one. Now, you have to delete this gate from the J frontier, because I mean we got this one and we have justified using 1 and 1. So, this gate cannot be used anymore for justification. Now, if you say that this AND gate output is 0, so there is 2 values of the singular cover. So, you can take any one of them for justification. This is a backward direction, because we already seen that in case of J frontier, that is by implication there is backward traversal and forward traversal. J frontiers corresponds to backward traversal. So, you can use any one of them, and then you have to delete this list from the J frontier, because this has already been used. Similarly, you can take for the OR gate. So, OR gate 1, that means there are 2 choices. So, you can take any one of them. So, OR gate 0, there is only one choice. So, after that is only the case, and this is for the fan out, it is very simple. So, if this is 1, so I mean this way, if this implication, so this one both of them has to be a 1 1. So, this fan out is very simple, because I mean this one to be a 1, then we know that actually it says that one of the this output is known, then you have to determine this one. So, if this output is known, then obviously this one will be a 1, because the J frontier definition says the output is 1 and the input one input or many inputs can be x. Okay. So, in this case you can see that this is the only one input, because the fan out tree. So, this can be set like this. And one more thing you have to know that this A, so whenever this justification has been done, so this has to be deleted. So, this gate has to be deleted from the J frontier list, because this gate already has been used for justification. Okay, so, sometimes you have both the values of x, so it can be justified, but sometimes it may not be possible, like for some reason, as I told you, it may be 1. Then what happens? It says that this x, this is not x, this is 1 say, but still it will be J frontier, because you have still this scope 1 x scope, because to justify the value of to be 0, then what you do, the x will try to make it 0, but then actually it is an inconsistency. Because making this x 0 will not help, because this also needs to be a 0, but the scope is not there, and then this actually net will be going to 1. So, there is a inconsistency. So, already we discussed that always J frontier, I mean J frontier have a scope to actually justify the output, but always it may not be helpful. But if in the case this x is 0, then this same gate still is in the J frontier, because the output is 0 and this input is the case. So, this input you make it to 0, and this will be solving your purpose. But always a gate in a J frontier may not solve your purpose, there may be inconsistency, but still a gate in the J frontier means there is some scope that it can be used for backward propagation or something, a backward propagation, and can be maybe used for justification, which may give you a successful result, but also may lead to inconsistency. Okay, so now, so this is what is being saying. The second gate has, like in this case, this is saying that the second gate. Okay, sorry, what does it say? So, the second gate has output 0. So, by singular cover we have 2 options for assigning the value to inputs, 2 options are shown in the right side. So, it is we are talking about this gate actually, these 2 gates. Okay. So, you see that the output is one kind of a thing over here. So, here this was also the case here. So, they are talking about this general case, that the second gate over here, it is saying second AND gate. So, it is saying that the output is 0 over here. So, there we are having 2 choices. Okay, so, which one to use? Also, you can also claim that there is a third choice, there is 0 and a 0. So, why not use? So, this is either use this or this. It is not saying that you do not use 0 0. Now, why is it the case? So, that is one question definitely in our mind. Similarly, in this case 1 1 is one choice which is left, so which you are not using. So, why we are not using, that is very important, we will see. So, that we could have another options to keep the input as 1, but however, this is avoided if both the inputs are fixed, then the flexibility is lost and cases of inconsistency increase. That is what they are saying, that if this is 0, output of AND gate is 0, you take x 0 or 0 x. if it is for an OR gate, sorry, if it is an OR gate like this. So, if the output is 0, output is 1, output is a 1 of an OR gate. So, you take x 1 or 1 x. They do not try to avoid 1 1 and 0 0 in this case. Now, why is it that? It says that if you hard code, okay, if by J frontier back propagation, I mean backward track, I mean when you are justifying using the J frontier gates. So, they say that if you put the value 0 0, you put the value 1 1, then actually you are trying to make some of the things hard coded. Some of the nets you are keeping hard coded, and then what happens if you hard code the nets too much, then the flexibility is lost and the chances of inconsistency are higher. So, we will see that by an example. So, what is the example over here? So, it shows that this is an AND gate. Okay, so small, sorry, it's a circuit. So, the stuck at 1. So, initially all the nets will be 0, the step 0. So, in step 1 we are stuck at 1. So, if you are stuck at 1, obviously you have to apply a 0 over here. So, 0 means normal case 0, fault case 1. So, it will be a stuck at 1. So, normal case 0, fault case 1. So, in this case, it will be a D prime. Okay, so, it is a D prime over here. Okay, now this is there. So, now what is now there is only a unique D frontier. So, this is the only gate where D effect can be propagated. So, it is a unique D cover. So, it is called unique D drive. So, obviously, this has to be taken. So, this second one. Now, this X. So, this gate is only in the D frontier. So, you have to propagate. So, now in this case let us see. So, this is the propagation. So, now in this case if you look at, so this is the only D drive. So, this is the only D frontier. Okay, now this gate, for this gate you know the output and both the inputs are, so it is D and both the inputs were X. If you look at this, the output is D prime we know, and both the inputs are 0. Sorry, both the inputs are X. Okay, so both the inputs are X. This was X. So, this and you have to get the output. This gate 1, say this is gate 2. So, output of the gate 1 should be 0. Okay, so now there are three choices basically, X 0, 0 x. So, these are the two choices which are allowed by definition. So, we are also asking the question that if you take both of them 0, what is the problem? So, let us first go for the choice x 0. We will see the problem later if we use this. So, x 0 may be there. Okay. So, we are using the choice x 0 because the output is okay. So, let this be the case. So, x 0. So, let us first look at these two choices and the other choice problems and all we will see later, that is hard coding of the signals we will see later. Okay. So, now in this case this is D prime. So, x 0 the choice they have taken. So, now if this is in the J frontier, this gate is in J frontier. So, the output is D prime. So, and we require a 0 over here. So, these inputs are not known, that is x and x. So, you can take x 0 or 0 x. So, they have taken x 0. Okay. So, now this is done. So, now this is x and this is the case. So, now this is the gate. So, now this is D prime, okay, correct. So, this is our D prime over here. So, now this effect has been propagated from this one. So, this is gate 1, so gate 2. Gate 2 was the J frontier. So, immediately this effect D prime has been propagated to this one, this gate is deleted from the D frontier. So, now we have to this net, this part will now become your J frontier, because we know that that this value has to be a 0, because for an OR gate this value has to be propagated here. So, this value has to be 0. So, now this net, this Fanout net will become a J frontier. So, we know that by this J frontier rule of the Fanout nets, so this will has to be a 0, this is to be a 0. So, now it is for backward implication and it is done. So, this way it solves a problem of your implication, that is already we have seen. This was the simple D algorithm, a basic idea of the D algorithm we have shown here. So, now we see that there was no inconsistency in this case. Okay. Now, so this was one example. Okay, so we will see later that what is the problem or what may be the problem if you try to hard code instead of this x 0, if you put this case, or if you put the case 1 0, this is also possible. Okay, right. Also you could have taken the case as because we require anyway this is a D prime. So, only we require a 0 over here. So, 0 x is a case, 0 0 is one case, 1 0 you can take, or also you can take 0 1. So, any one of these hard coding case, sorry, this is 0 and this is 1. So, any one of these choice, like the choices as x 0, 0 x, 0 0, you can also take 0 1 and 1 0. So, any of these choices like 1 2 3 4 5 choices you apply over here, you can get the value of 0 over here, correct. that is the output of this gate, you can get the same, I mean this is this any of the choices if you apply in this case, you get a 0 over here. So, this you will get a d prime over here. Now, this will become your d frontier. So, you have to propagate the value. So, it will become d frontier. So, it will propagate the value here. So, once this I mean d prime is propagated here, this will no longer remain the d frontier, then you require a 0 over here, and then this will become your j frontier, and then x will get some value kind of a thing. So, in this example we have seen there is no inconsistency, because we have used the case of x0 or 0x whatever that was being allowed. So, later we will see what may be the problems if you try to use the strict cases like 0 0 1 0 0 1 instead of keeping the x, that we will see later. But this was just a scheme, this was just an example to illustrate how the implication procedure works, and also a miniature version of or a very broad version of D algorithm. Okay. So, some more definitions and actually examples of the definitions and procedures we have used. So, say for example, in this case same like it is an example of a D frontier. So, I mean if this is a D and this is a 1, so this is the unique. So, you can drive this one from here. So, the output is x, and you know that the input, this input is a D. So, you can easily drive this value of this one from here. So, again the D frontier has to be lost. So, that is you are propagating the value, then this is a lost. So, other things are very straightforward, this is just a value computation. This is another example, we can also, I mean very simply it says that it is a 0 and 1 and a D. So, the output will be say for example, the output is actually in this case the output is a D frontier is this one. So, A is a D frontier because this D is over there, this output is x. So, you can easily propagate the value as 1, but in this case again this is a very important point, you have to note that this is a D frontier like J frontier. Sometimes always all gates in D frontier or always all gates in the J frontier may not help, because we have seen many examples of J frontiers in which case there were gates in the J frontier, but it was not helping. Similarly, this can also happen in case of D frontiers, like in this case this is an OR gate. So, this is the D. So, it is D, so the value can be propagated, the output is x. So, the value of D can be propagated, so it can be assumed, but the another input is 1 because of some reason. So, this gate is in D frontier true, but the output is 1. So, the value of this one is not propagated, and again this gate will be lost from the D frontier. So, you would consider this gate to be in D frontier because by definition the output is x, the input is D. So, there is a scope of propagating the value, but because this input is 1, so nothing could have been done. So, as this gate was it was true that this gate was in D frontier, but we could not do much. Now, why we could not do much? Because the value of D was not propagated because of this one, but still you have by definition such gates will be in D frontier, but when we will be trying to propagate the value to the output, we will find that the output is not propagating. So, such type of gates are examples of gates in D frontier which is not of much help. Similarly, also like definition we have also seen that some cases of gates in the J frontier which we thought that somehow the value the value could be justified, but it could not be because of this. For example, like already many times we discussed in the lecture that it is we require a 0 over here, sorry, we require a 1 over here. So, this was x and this was 0. So, this was x. So, and one input is 0, the output required is 1. So, we also consider this gate as in D frontier because there is some scope that we may set this x to get the value 1, but in fact this will not be successful because this one input is 0 which will make the output of the gate as 1. So, this was an example where a gate is in J frontier but not helping it, and similarly this is an example of a gate in D frontier but not helping in the propagation. This is how it is requires to be. So, if it is 0 then the D effect will be propagated and then this one will help in this one. Correct. So, I mean, so sometimes there are lots of gates will be in, so in other words there will be lot of gates in J frontier and D frontier, but they will always not be successful or always not be, I mean, lead to fault propagation in case of D frontier, and always they may not lead to successful justification in case of J frontier. So, there will be lots of gates in J and D frontiers, but some may be successful, some may not be successful. That is what is being shown by the illustration in this example. So, before we quickly wrap up with the definition, so there is one more definition that is actually called the X path. So, as we already discussed that all the input nets of your circuit. So, initially we mark it as x, then by some, if we know the values of some of the nets, and that is by implication we try to find out the values. So, for example, let us have this circuit. So, let us we know that for some reason we know that, let us assume that we know the value is 1 1. So, by implication this one will be 1. So, let this be x and D. So, the output will be x. So, this is the case for, and by some reason let us assume that we know the value of this one to be a 0. So, the output is 0 to be known by implication. So, this value let us assume by for some means we assume that they are not primary inputs, maybe by some other combinational logic as input or because of some other reasons we know that the value to be 0, then by implication also we know the value to be 0 directly. Now, in this case you see that there is only one value as x. So, in this case you can consider that this is the D frontier because this is output is x, so you can propagate the value of this one can be d. So once it is d, then this gate will become j frontier, then you have to get the value of x as 1 and so forth. This is how our implication procedure goes forward. But for the time being, so what it says that in this case if you look at it quickly, so there is one x over here, so if it is x, so there is one more x over here, and this is an inverter, so this is one more x over here, and let us consider these are the primary outputs. So there is a path, okay, from this D frontier, there is a path from here to the primary output where everybody is at x. So there is at least one path. So if there is no path like this, say for example, had this gate not been there, so had this gate not been there, then what will happen? There is no path from this D frontier which is all covering through the x gates, and the output of the gates are x. So it will come here, and after that this one is also known and this one is also known. So after this the fault propagation will definitely be terminated here. So that is what, in other words, what we are saying, that if there is a D frontier, or if there is in this example is of getting a single D frontier, so it says that from this D frontier there is at least one path where all the outputs of the gates are x. That means this is the only path which can be used for propagating the fault effect, because either this x can be D or D prime, this x can be D or D prime, so this x can be converted to D and D prime. So this fault effect can be propagated only through this path, but this path and this path, the outputs are not x. So that means if you cannot do anything, and if this x path is not there, the fault propagation will be terminated at this path or this path. So it says that x path is a path of consecutive nets in the circuit whose output values are x. So let A be in D frontier, this is the gate A, say in D frontier. The outputs on the inputs can be propagated to the primary output O only if there is a x path from A to O. So that is saying that this is the input and this is the output. So from the gate with the D frontier, that is where the fault effect is there. So that effect can be propagated to the primary output if and only if there is a path of gates whose outputs are all x, because this x can be converted to D or D prime and the fault effect can be propagated. But if there is no gate, no path like this, then we know that the output, then the idea is that you cannot propagate the value to the output, and actually in fact you are lost by this one. Okay. So, so that is all the definitions we require for knowing the D algorithm. Okay. And the next what we will study is actually the D algorithm in detail, that is your circuit netlist and primary output values and expected values of the primary outputs. That is circuit netlist with one stuck at fault and the output and the primary input values required to test the fault, and what is the expected the primary output. That is your automatic test pattern, we call this ATP. So in the next lecture, using all the definitions we have studied today, we will try to elaborate and look formally into this D algorithm using the definitions and the procedures which we have discussed today. So using that, we will try to formally articulate D algorithm, and then what we will do, then we will very what do you call, in details we will take an example and try to find out how D algorithm basically works on that algorithm using implication, J frontier and D frontier propagation. So that is what we have for today. In the next lecture we will go in elaborate D algorithm with examples. Thank you.